This PowerPoint perspective was designed to, or on perspective, was designed to be a standalone item, but I believe it will be beneficial to add some audio to it to complement what the visuals are. I set this up in the drawing room because that's the environment that you would be drawing, or most of you will be doing this drawing assignment in. There are some basic concepts, rules if you will, about linear perspective that you need to have a pretty good handle on. And so let's take off here. I set up two boxes on a table in the drawing room and went ahead and did a really simple it's a 3-point linear perspective drawing. Well, technically it's a 5-point linear perspective drawing, but it's based on what is fundamentally called 2-point linear perspective. I'm going to show you how to locate different vanishing points. It will cover most of the issues that you'll be facing in learning linear perspective. So what we're looking at is the finished product in line only, and I'm going to walk you through how we got to that point. First of all, linear perspective is what happens when you project any image of the real world onto a two-dimensional surface. A drawing, a painting, a television screen, a movie screen, an oil painting canvas, a watercolor sheet of paper, any of those two-dimensional surfaces. What is created when you project the real world onto a two-dimensional surface is actually a distortion of reality. Well, sort of. It records how we perceive reality, but there's some information there that isn't exactly right when it's projected. Well, we call these distortions perspective, and linear perspective shows up in particular when we're working with geometric shapes. What we're wanting to find is the vanishing points of the geometric shapes. Vanishing points are where parallel lines converge. That's the distortion, if you will. In reality, parallel lines never converge. No matter how far you project them into the distance, they don't converge. But they do in a photograph or a drawing of the real world. And the most important rule is that all parallel lines converge at a single vanishing point. As you can see in this illustration, we've got two boxes. One box has a couple of flaps up, the other box has the flaps down. And the green lines on the left are converging off of the picture plane or off of the computer screen in this instance. But they're converging at a point on the blue line, which is the eye level line, commonly called the horizon line. The red lines over on the right are projections of three of the parallel lines of the short box, and they too are converging on the horizon line or eye level line. The tall box, the shorter side of the tall box, those three yellow lines are converging where we can see them at the vanishing point for those three lines. So that's the basic concept that we're looking at. Parallel lines converge at a vanishing point. But where is that vanishing point and how do you find it? Well, let's start by placing the drawing on a piece of paper. One way to do that would be to draw a line near the top of the paper, a horizontal line all the way across the top of the paper, and call it your horizon line. and that will work in many instances. But it may or may not be the best placement of a line for any given drawing. So one good way to approach this would be to place, say, the center or that tall front vertical line of the larger box, and place it on your paper where you want it and the size you want it to kind of establish the excuse me, to establish the size and placement of your finished drawing. And then from there, extrapolate from that where your eye level line would be. Well, you can't just draw a line anywhere above the box or above where you put that corner of the box. You have to establish what the real world distance is. And so what you need to do is measure it. I found that image of a seated young man out on the internet when I did a Google search for seated figures. Found a site that had advertised free seated figures. And borrowed him, photoshopped him into one of our chairs, and I literally put a piece of blue tape, masking tape, on the window shade on the opposite side of the room. And I placed that the same height off the floor as my eyes are when I'm seated looking at these boxes. So that blue line across the room is literally my eye level. It's the horizon line of my drawing, but it is literally my eye level. That is what a horizon line is. We call it a horizon line because if you think about your eye level being 5 foot, 5.5 feet, or if you're really tall, maybe over 6 feet, your eye level may be that far off the ground. But when you're looking at that distance off the ground at the horizon, 6 or 8 or 10 miles away, it's infinitesimally small. And so it's essentially the horizon. But you don't do many drawings of the desert. Well, some people do. But the desert or maybe the ocean is the only time you're going to see a perfectly flat horizon. So I will use the terms horizon line and eye level line interchangeably. So that's what that short blue line is that I've superimposed with the red line going all the way across. And so that is the counterpart in the real world to my horizon line in my drawing, which we'll get to in a minute. I can hold my arm out straight, hold the pencil in my hand vertical, and measure the distance from that red line down to the corner of the box. Or I can turn my pencil sideways and measure the width of the box, or the width of a flap on the box, or the width of the table. All measurements can be taken from the real world. However, there are a couple things you always have to pay attention to when you're taking measurements from the real world. Number one is you are measuring on a picture or on a plane. Think a piece of glass out in front of you. And so you always have to measure on the same plane. That means you have to always be sitting or standing in exactly the same position, not leaning forward or leaning backward very much. And your arm has to be at arm's length with the elbow locked straight. Because if you bend your elbow, that distance between your eye and the picture plane that you're measuring on are going to be different each time you put your arm out. So there's two constants. One is your station point where you're standing to the subject, and the other one is the distance from your station point to the plane you're measuring on. And these two photographs illustrate that. That milk can sitting out in the yard, I can hold my hand out in front of me and measure it, marking the top with the top of the pencil, the bottom with my thumb, and then I can hold my finger on that point on the thumb, or on my thumb on that point of the pencil, my apology, and use that to measure the height on my paper. Or I can measure the width of it. Well, so here I am measuring. Notice the elbow is straight. I cannot emphasize how important that is. Like I said, it's sitting in a chair in the room. You need to be sitting in this chair in the same spot when you're measuring a box in the room, not leaning way forward or way backward. Keep your arms straight. So the diagram on the right, if you ever see somebody, an artist in a cartoon or somewhere taking measurements like that, they don't know what they're doing. Arms straight, always from the same station point. So I mentioned that it's like you're measuring on a window. So I superimpose this transparent sheet of glass. And so that's what you're measuring on. It's invisible to you, but it's out there, always in the same place. Exactly where that pencil is when you hold your arm out straight. So you know you can be consistent measuring on that picture plane. So back to measuring the box. I've located where I want the top corner of that larger box to be on my page. And I know about what size I want it to be. But where do I put it from the horizon line? Well, when I measure that distance here in the room, it is 3 inches. On the picture plane I'm measuring on, remember, holding my arm out straight, it is actually, I used a ruler to actually measure that distance, 3 inches between the eye level line, the blue tape on the other side of the room, and the corner of the box. It was 3 inches. Well, 3 inches doesn't work really well in my drawing. It's going to put the box too high in my drawing. So I simply converted that to 6 inches in my drawing. So I measured down 6 inches and drew the vertical line for the front of the box. Now the box is a little bit further along right now than that, but what I've established is a 1-to-2 ratio. That means that any measurements I take out there in front of me, or on the picture plane I should say, I'm going to double those on my paper, 1-to-2 ratio. The other thing that is important to notice about this is that the left vanishing point is off of the picture plane. And let me back up here. Yeah, I'm ready for that. The left is off of the picture plane, but I want to talk first about the angles. What I need to do is establish what the angle is between a horizontal line at the base of my box or the top of the box. It wouldn't matter where you start. And I want to measure that angle. And I can hold a ruler out horizontally and tilt it back and forth to replicate that angle and then replicate it down on the paper. Or I have a tool that I bring to class sometimes, piece of plexiglass with a bunch of colored angled lines on it that you can use to line up with the subject, and you can see which of the colored lines line up with the actual object. Well, I've established that the two angles of that box are about equal, one going to the left and one going to the right. Unfortunately, one of those is off of the screen, or off of the table, I should say. So I borrowed another drawing table, and you might have to do this in the classroom with social distancing this semester. But you may have to borrow a table or even 2 tables, so you have 3 tables wide. Or you can take a piece of mat board and jury rig it onto your table, extending the width of your table in order to actually find the vanishing points. So all I've done here is extended, I've drawn the angle to the left and extended it all the way till it intersects with the horizon line, and made a little red dot here. You'll probably make an exit, an X. Then I did the same thing on the right and where the line intersects with the eye level line or horizon line, put a mark. Now we have our left and our right vanishing points. And this problem with it being off the table, I could have drawn a lot smaller and brought them both on the table, but I wanted that drawing to be a certain size, so that forced it off of the drawing board. Well, I'm going to take a little bit of a sidetrack here and tell you how you can use a vanishing point off the table without actually finding it physically. Well, you need to find it initially, but you don't have to keep using it. You can move that table back so the other student has it. If you cut a rectangle out of mat board and tape it down on your piece of drawing paper, similar to what I've done here, that vertical rectangle, so it overlaps with your horizon line, maybe in the middle, maybe a little bit above your horizon line. Tape it down and then use a pencil and a tack with a piece of string. Anchor the tack in the left vanishing point in this case, and draw an arc with your pencil with a string attached so you have the correct distance, but draw an arc with that pencil string thumbtack gizmo, or if you have a large enough compass, just use a compass. But draw an arc on that piece of paper. Then take it off of your good paper, off your drawing table, put it on a surface you can cut on, and with an X-Acto knife very carefully cut along that arc. Cut that rectangle into two pieces. After you've cut it into two pieces, you can go back and glue the larger one, the left one, not glue it, tape it down so it can't move, tape it to your drawing, and with the other one lined up where it originally was, tape or glue, attach a long thin piece of mat board to it. That's going to be the line, the tool to draw your perspective lines with. Once you have those three pieces of paper, actually the one on the right is attached as one and the one on the left is one. When you move that bar that you created along the arc, it is always pointing back to the left vanishing point. So you can use that tool instead of a long ruler and a vanishing point off of your drawing board. So just a nice little way to use a distant vanishing point. Well, let's get back to the drawing. So I have my left and my right vanishing points, and I've now created this little simple box. I should interject now, or I am going to interject now, that there really should be another vanishing point, and you may be way ahead of me on this. The vanishing points and this whole perspective thing has to do with the monocular clues. So need to, again, take a little bit of a time out and explain what the monocular clues are, because those are the only tools artists have to work with to make the real world look real on a two-dimensional surface. So, what are the monocular clues? First of all, they're called the monocular clues because you don't have to have binocular vision to observe them. God gave us two eyes for a very important reason. Probably not in case one gets put out, you'll still have one, although that isn't nice. But it gives us binocular vision. Our brain is being fed with two simultaneous images. Maybe in class I'll go into that a little bit more and how the 3D movies are created as a result of that concept. But our brain takes those two images and synthesizes them into one image. Well, so you don't need binocular vision to see the monocular clues. They are, quite simply, size. We call it relative apparent size. Things further away appear smaller on a picture. Position. Things further away are higher up on the picture plane. Well, that is true below the eye level line. Above the eye level line, things further away are lower. Think clouds. On a beautiful blue sky day with a lot of cumulus clouds, the distant clouds are lower, closer to the horizon. But the railroad track gets smaller as you move up. So the relative size switches or the relative position switches with whether it's above or below the eye level line. Overlap, it's kind of a no-brainer. If one object is covering another object, overlapping in front of it, we know it's closer. Light and shadow, as artists, we use this one a lot, and on the last two slides we'll deal with light and shadow on this assignment. But quite simply, light falling on an object will create cast shadows and form shading. And you also have the ambient light, whatever the light is in the room or in the space, the overall light. So you have a variety of types of light, but light and shadow. An atmospheric perspective, also known as aerial perspective, is what happens with distant mountains. They're bluer, they're fainter, they lack detail. Atmospheric perspective. Those are the 5 main monocular clues. There is one more, and it's a little hard to even find examples of it. The vast majority of ways we interpret three-dimensional depth are with those 5 I just mentioned. But sometimes there's a context factor that is independent. Well, it's indirectly dependent on the monocular clues. 2 different monocular clues create a context that we can read. So, linear perspective is fundamentally using size and position. Those are the 2 main monocular clues we're dealing with now with linear perspective. So back to my drawing. I took this photograph to illustrate my drawing in the foreground and the boxes in the background to put the 2 in context. My blue tape is actually barely visible at the top edge above the boxes. But look at my perspective box. That is the same box that I just showed you. It's distorted now. It looks like that little box that elephants put their feet on in a circus. It's wider at the bottom. Well, it isn't really. When I took the photograph, the drawing is laying flat on the table, so the bottom of the box is closer to me than the top of the box, and so it is larger. So what we have is linear perspective messing with the box that I drew in perspective, making it now appear to be incorrect. Well, that does bring up another point. Since linear perspective messes with the width of the top versus the bottom, let's talk about that third vanishing point. In this instance, I made the 3 vertical lines converge slightly. This is the way it really ought to look. The reason for that is that the top 2 edges of the box, or the top 4 edges, the top 2 edges on this side of the box are closer to me than the bottom 2 edges at the bottom of the box, because I'm looking down at the box. So the relative distance to the top of the box is less than the distance to the bottom of the box, which means, according to the monocular clues, the bottom's further away, so the bottom sides have to be shorter. And so we need that third vanishing point, because in fact, those 3 vertical sides, actually the inside of the back corner, which isn't drawn yet, those vertical lines are going to converge way down below the drawing. But it's not going to be practical for me to actually locate that vanishing point. So I just guessed. I fudged. and made up a vanishing point and made it feel right. Made it so it looks decent. So here's the finished 3-point perspective box. Not bad. A couple of things are bothering me about it, but we're going to move on. So we have 2 boxes, not 1. We need a new set of vanishing points to establish the other box on the paper. That other box deliberately is not parallel to the first box. If I set the 2 boxes so they were lined up with each other, parallel to each other, I could have used one set of vanishing points for both of them. But I did it this way because I wanted to talk to you about a second set of vanishing points. In this case, both vanishing points for that smaller box, shorter box, both vanishing points ended up off of the paper for several reasons. But regardless of the reason, they are both off of the paper, which does point out something that I need to mention. The left vanishing point for the tall box is to the left of the left vanishing point that you can see here of the short box. That short box is rotated very slightly to the right, clockwise. As you rotate the box clockwise or counterclockwise, the vanishing points are going to move left or right along the horizon line. Important concept relative to perspective. So now I have a set of new vanishing points for this box. And adding the third vanishing point. By the way, both the boxes share the bottom vanishing point because all those lines are vertical. Neither box is tilted in space. Since all, there's 1, 2, 3, 4, 5, 6, 7, 8 vertical lines, they're all visible. Every one of them should be pointing to a single vanishing point somewhere below where I'm sitting. Well, I just guessed at where it might be, but now those boxes look pretty decent. So let's throw a curve into this. It's not a curve, but it is like a curveball. The boxes, cardboard boxes, have lids, and I deliberately tucked the lids of the tall box into the box so they wouldn't be part of the scene. Could have left them there. It would have complicated this assignment. I wanted to shorten the length of this presentation, so I only left 2 lids open. Well, in fact, I only left 1 lid, the one that you see the vanishing points for. The other one I opened up on the paper by drawing it in. So those blue lines are pointing now to a vanishing point up above the right vanishing point. The nice thing about tilted surfaces, it might be the roof of a house or the lid of a box when you open a lid of a box, or the tilt of the roof, the vanishing point for that sloped surface is going to be directly above the vanishing points for the object itself, whether it's a house or a box. And so by drawing a vertical line above my vanishing point for that box, I actually just realized that I made a mistake on that, and if you're really sharp, you'll have caught it. I'm not going to tell you what it is, so see who comes back with me on it. But anyway, you draw a vertical line directly above your vanishing point, establish the angle of one side of the flap that's open, draw it till it intersects with that vanishing or with that vertical line, and then mark an X, and every other line goes to that vanishing point. This is really handy to know with shingles on a roof. Once you've established the vanishing points for the roof line, the angled roof, all of those shingles need to go towards the vanishing point. So here we have the completed 2 boxes, just blocked in, if you will, with the light lines going off to the different vanishing points. We have an extra set of an extra vanishing point now for that lid that's lower. And the vanishing point there would just be lower on that vertical line. So there's a completed 3-point perspective of boxes waiting to be rendered with value, light and shadow, to give them greater illusion of reality. So I did a quick pencil sketch to throw in that monocular clue, light and shadow, and you now see that we have 4 of the 5 monocular clues. Relative size, the perspective is causing it to get smaller as it moves away from us. The box, the back side of the box is shorter than the front side. Position, the back of the box is higher on the picture plane than the front of the box. In fact, the short box is a little higher in the picture plane. You see where it sits on the table. It's higher up. Immediately tells a viewer that it's further away. And overlap. The tall box overlaps in front of the short box slightly. So that's another clue to three-dimensional space. And then when you throw in light and shadow, and we have here the ambient light of the atmosphere, plus the surface values created where the light source is being blocked from some surfaces, and the cast shadows of an object on another object. So that's all there is to it. There's the same objects rendered with a computer instead of pencil. So that is the end of the perspective PowerPoint. Thank you.